Hey, digital electronics, it's Miss Jo here, and today we're going to learn how to use the multimeter in Tinkercad. So I have my task 7 up for you guys to see, and we're going to explore to see if this capacitor is actually discharging to help light up this LED. So to find your multimeter in Tinkercad, it's all the way on the bottom of your circuit components. I've already dragged mine out into the workspace, and if I start my simulation, you can see that your multimeter can measure your amps, so it can be an ammeter, it can measure volts, so it can be a voltmeter, or it can measure resistance, so it would be an ohm meter. So here we have this lovely circuit, and right now I have both the capacitor and the LED in the off position. And since the LED is not directly connected to the power strip, only the capacitor is, the whole purpose of this is that the capacitor would supply voltage to the LED. So if I were to turn on this LED, you can see that it does not turn on. Okay, so it's off in the off position. Now, if I turn on my capacitor, I can assume, since my capacitor is connected to this 9-volt battery, that the capacitor is charging right now. So it's going to charge up to whatever its capacity is. In this case, it would be 9 volts. And my light is still not off, or still not on. But if I were to switch my little switch on, you could see that it's very bright. So it is continuously getting energy or voltage from this capacitor. So what I would postulate is that if I were to turn off my capacitor, then it would continue to supply voltage to this LED, but the LED would slowly fade out because the capacitor would drain since it's off, and it would no longer be getting recharged from the 9-volt battery. So if I test that, I turn this off, and you can see my LED is slowly starting to dim. It is very dim right now, but it is still kind of dim. So we'll see how long it takes. Now, if I were to turn this off, it would completely black out, so you can tell. And then if I turn it back on, you can see that the capacitor is still slowly discharging. Okay, so to actually prove that this is happening, we can get our capacitor, and we can measure the voltage across the capacitor. So we're going to change this to voltmeter, and I'm going to get my negative terminal of my voltmeter to come over here. Oh, I need to stop my simulation. And I'm going to click on the negative, and then I'm just going to put it on terminal 1 of my capacitor, and then I'll change my color to red, and I will get the positive one over here right there. Oops. Okay, sweet. So now I have set up my voltmeter. I don't know why that didn't turn black, but now it's black. Okay, so I'm going to now start my simulation, and I can see that my capacitor is at 0 volts, so it is not charged. If I turn this on, but let's go ahead and turn the LED off. Okay, so it's in the off position. And if I turn this on, I can see that it has charged. And it looks like I probably put it's -9 because I probably put these two things in the wrong place. To prove that, let's go ahead and erase these two things and just switch them. So this -1 should go to terminal 2, and this positive one should go to terminal 1. I just had them switched. So now if I press start simulation, it should read positive 9 volts, and I'm correct. Okay, so this is charged, and if I turn my LED on, it is nice and bright because it is getting the voltage from that battery. Now, if I turn this capacitor off, my LED will start to fade, and you should see the number on the voltmeter starting to decrease. So it is discharging, and you can see that it discharges pretty fast at the beginning, and then it goes really slow. So your LED is going to stay dim for a really long time because now it's going really slow. You can tell it's going in the hundredths, taking a while to discharge. So if I wanted to, I could just turn the LED off, and it would no longer be getting charged from my capacitor, but you can see that my capacitor is now stopping at 1.53 volts. Since there's nothing to supply that voltage to, it keeps that charge right there. If I were to turn this back on, it would be dimly lit, and it would start to decrease again. Turn it off, and if I wanted to recharge my capacitor, I could turn this on, and you can see that it recharges really quickly. Okay, so that is how the ohm meter works. If you wanted to measure resistance, you can put your two terminals on either side of the resistor. Oops. And I don't think that went, so let's try that again. We want it to go right there, and we want it to go right there, and we want to put it on resistance. Oh, it looks like you have to maybe change the meter first. Well, it doesn't like me right now. There, it's on resistance now. And stop simulator. Okay, let's try that again. It's on resistance now. It didn't want to change. It was happy being a voltmeter. But now it is an ohm meter. If I press start simulation, oh, I did it on the wrong thing, didn't I? I'm sorry, y'all. Okay, let's try that again. Go away. I don't want to know the resistance of the LED. I want to know the resistance of the resistor. Boop, boop. Okay, start simulation. And I get 1,000 kilo ohms. If I stop my simulation and I double click on my resistor, that is indeed how many kilo ohms that resistor is valued at. Okay, so when you're using the ammeter, it's a little bit trickier. So you have to kind of think about where you want to know where the current is going through. Because what the ammeter does is it actually bypasses the current. So you have to put it on either side of the element in which you want to know what the current is going through. Let me show you with a simple example of my task 1. So in this, I have a 1 kilo ohm resistor, and I'm going to set my power supply to 5 volts. Okay, and so if I want to know what the current is through this resistor, through this LED, I'm going to go ahead and connect either of my terminals to the LED. And so what that's doing basically is it's going through here, right? And it's going to go through here. And then when it gets to this point, instead of going through the LED, it's actually going through the ammeter. And then it bypasses it, and it goes to the other side of this terminal, and then it goes through the resistor, and then back to the power supply. So when I start the simulation, you're going to see that the light bulb actually doesn't go off, but it measures the current of 5 milliamps, which is the right current because this is a 1,000 ohm resistor, and I'll show you the work in a second. Okay, here's that problem. I had volts 5, 1 kilo ohm, and so that's 1,000 ohms, which is 5 divided by 1,000 is 0.005 amps, which would be 5 milliamps, and that's what the ammeter read. But if I were to notice the light bulb is not on because the current's basically not going through the light bulb or the LED, it's instead going through the ammeter. If I were to stop the simulation and erase my 2 wires and press start simulation, you'll see that my light bulb does indeed light up. So another example of this is like if I bypass the resistor and the LED. So let's say I just want to know what the current is between here when the power supply goes into its first breadboard hole to here. Okay, so what's going to happen is it's going to go through here, and then instead of going through the resistor and through the LED, it bypasses and goes through the ammeter through here and then goes back here. So it's basically not the current's not going through the resistor or the LED. And so this should just show what the voltage is. So if I have my voltage set to 5 volts, since there's no resistance, then and V or I equals V divided by R, you should see that it's just 5 amps because I have 5 volts, and I don't know why the voltage went to 0, but so it's bypassing the whole, and this doesn't actually light up. If I stop the simulation again, I can light up my light bulb again. Okay, so the moral of the story is if you're using the ammeter, you have to put the 2 little terminals directly on either side of where you want to see what the current is going through. If you don't do that, it basically will bypass anything upstream or downstream of where you place the 2 terminals and just read the current through that area. Okay, hopefully that kind of makes sense. Okay, so for today's assignment, it's found 9.925. We're going to use the multimeter And we're going to do some circuit practice problems, and then we're going to use Tinkercad to check our work. And so I'll do one example for you. So you're going to do 4, 5, 6, 7, and 8, and I will do maybe 1 or 2 for you. So the first one, it says using the laws of circuit theory, so that's Kirchhoff's law. We're going to calculate the total resistance, the total current, and then the voltage through R1, the voltage through R2, and the voltage through R3. So I'm going to redraw this and calculate it for you. Then I'm going to make it in Tinkercad, and then we're going to check our work. Okay, let's do number 4 together. So you're going to do these in your engineering notebook. So you have a 9-volt battery. I'm going to redraw this, and you have a 470 ohm resistor. And then you have a 1.2 kilo ohm resistor. And then it comes around and you have a 270 ohm resistor. And then it comes back to the battery. Okay, so the first thing you have to do is figure out the equivalent resistance, but all 3 of your resistors need to be in the same units. So your kilo ohms are 1.2 kilo ohms. So 1.2 kilo ohms, let me do that again. 1.2 kilo ohms, we're going to move our decimal over 3 times, 1, 2, 3. So that's going to be 1,200 ohms. Okay, just went 1, 2, 3, and that's regular ohms. Okay, so now we can figure out our equivalent resistance. So Req for a series circuit is just adding the 3 resistors. So we have 470 ohms plus 1,200 ohms plus 270 ohms. And do I have a calculator? No, I don't. Oh, because my calculator is on my phone. That sucks. Okay, let's do this real quick. So we have 1,200 and 470. 7, 4, 5, 6. And then plus 270. That's 7 times 2 is 14. 6, 7, 8, 9. Oh, that was not fun. Req is equal to 1940 ohms. Okay, so the first thing it wants us to find is the total current. So we have our little ohms triangle, VIR, and so our total current, I total, is equal to our total voltage divided by our Req. Voltage total divided by Req. So we have our voltage is 9 volts and our Req is 1940. And I'm not even going to pretend like I can do that by longhand. So I shall use my handy dandy computer. The total current is equal to 0.004633918. But we have to make sure that we're doing proper sig figs and scientific notation or engineering notation. So we're going to go 1, 2, 3. So it's going to be 4.6 milliamps. Right? 4.6 milliamps is my total current. And then what else does it want us to find? It also wants us to find, so we found this. This is the first thing it wanted us to find. It wanted us to find this. I used engineering notation. And then the voltage across the 3 resistors. So the voltage across resistor 1, so VR1, is going to be my current. And since it's a series circuit, the current's the same everywhere. But I have to put this back in regular amps because Ohm's law equation works with the 3 units in their base form. So we're going to go back to 0.0046 amps times 470 ohms. So let me get my calculator again, and I have 0.0046 times 470 gives me 2.162 volts. And we'd probably just do 2.16, and that 2 would not be significant. The voltage across resistor 2 is, again, I times R. My I is going to be 0.0046 amps, and my resistance for my second one is 1,200 ohms. So let's do that one. We have clear. Let's have 0.0046 times 1200 gives me 5.52 volts across resistor 2, and then voltage across resistor 3 again is my current 0.0046 amps times 270 ohms. Okay, clear. 0.0046 times 270 gives me 1.242 volts. Okay, and these should add up to 9 according to Kirchhoff's law. So let me add those up real quick. I have 1.242 already in my calculator. I'm going to add that to 5.52, and then I'm going to add that to 2.162, 2.162, and so my voltage drops. It is equal to 8.924, and so we can round that to 9 volts. So that checks out. Okay, so now let's set that up in Tinkercad and check all of these boxed answers.